Okay, welcome again to now the second part of sequences and series. And today, as I said in the first video, in part one, that we will be looking at the questions and we'll be answering them, right? So let's start off by talking about obviously just a quick recap that we have three different types of sequences. But there's sequences and series, and a series is basically a sequence, but the difference is that now we are adding each individual term to maybe an nth number, right? So we have a quadratic, we have an arithmetic, and a geometric, and you saw the formulas and how you should possibly do it in the first video. So let's begin with question 2. So this question 2 comes from actually a past paper, which is a November past paper of grade 12, 2015. Right. So this question 2, it says the following geometric sequence, right? And we know what a sequence is. It's just a list of numbers that's been placed in some sort of order or in no order at all, right? So we have 10, we have 5, we have 2.5, and we have 1.25. And then they give us some dots, meaning that it continues to a certain nth term or maybe to infinity. So 2.1 says, calculate the value of the fifth term. So if they're asking us to calculate the value of the fifth term, and that is T5, or the fifth term, you can just say this fifth term of the sequence, what can you do? Now the first thing you can do is, since they already kind of told you that it is a geometric sequence, then you already know what you really need is the ratio, right? You need the ratio, this R there, which is T2 over T1. But it doesn't have to be T2 over T1. It can also be T3 divided by T1 or T4 over T3, right? It has to just be two consecutive terms that you're dividing to give you your R. Now, when you do that, what do we get? I took T2 over T1, and that's 5 over 10, and that's just half, right? So R is half, and we know that the general term, the general term of the geometric sequence or pattern is that it is A times Rn minus 1. So we need A, and we know that A signifies the first term. So the first term here is 10. So in actual fact, we have half as R and A as 10, and then we just plug in the formula. We write down the formula first, then you plug in the formula, and then there's your 10, and then there's your half, and then you have your general nth term, right? So this is the general nth term. But the question is not that you want your general nth term, but you actually want T5. So then you plug in 5, the fifth term, 5 at your n, and then you calculate that, and you'd see that in actual fact, when you put in the 5, it will give you 0.625 or 5 over 8, right? But it's best maybe just to put it at 0.625 because here you can see they use decimals as well. Okay. Yes, this is one of the ways you could do it, but the other way is if you could have noticed that in actual fact, 10 is divided by 2 to give you 5, and 5 divided by 2 is 2.5, and 2.5 divided by 2 is 1.25, and 1.25 divided by 2 will give you 0.625. So it's either these two ways, but both of them are quite correct, and it works. So we go to this next question, and it says 2.2, determine the nth term of Tn in terms of n. And we've already done this in actual fact in 2.1 when we wanted to calculate the fifth term. We used the formula, and we had already gotten our A and R. So in actual fact, we just rewrite it again, the Tn, and then Tn is 10 times 1 over 2 n minus 1. And that is our Tn, right? Okay. Now, here comes a more thinking question, or a more interesting question. And the question says, 2.3, explain why the infinite series, right? So this goes all the way to infinity. 10 plus 5 plus 2.5 plus 1.25 converges, right? They're asking us why it converges. But remember what we said about in the first video is that in actual fact the sum to infinity for a geometric pattern is given to you by the sum to infinity is equal to a all divided by 1 minus r, right? And the condition for this to work is that your terms, the terms of convergence, the condition for it to work is that your r has to be in between -1 and 1, meaning that in actual fact it has to be a number that is between 1 and -1. So it could have been 0.03, could have been -0.9 or something like that. Okay, so in actual fact in here we do know that our r is actually 1/2. So r is in between -1 and 1, therefore it should converge because of that reason, right? And you can see here I said the given infinite series of a geometric series is known that the sum to infinity is all over 1 minus r is convergent when r is between 1 and -1. So which with that it is given that the geometric series that where r is actually equals to 1/2, that is between -1 and 1, therefore the geometric sequence is convergent. And that is the reason that you're supposed to state, right? So basically what they'll be looking for here is two things. They'll be looking for you to actually show that in actual fact the r that you have calculated falls in between 1 and -1, and then also state that because of that it is convergent. The sequences the series, not sequence. The series, not the sequence. The series, right? So it's series, not sequence. And why is that? Because the sequence is just a list of numbers and it's not adding together, right? Okay. And here's a small drawing that I drew. If you think about it, geometric sequences or geometric series and sequences, they're quite interesting for the simple fact that we know this type of function, and this type of function is what we call an exponential function. And you know with an exponential function that it has an asymptote, especially when the r is a fraction, right? Or any number that is between -1 and 1, and we know that this would make it slant in the other way, right? It slants in the other way, and you know that generally this would mean that in actual fact it does sort of move towards a certain number, and that is what convergence means. It means that we are moving towards a certain number, and that number, the more we keep adding and adding and adding, comes closer and closer and closer. And the other idea is that in actual fact, when we say something moves closer and closer and closer, and we talk about functions, especially exponential functions, we are literally talking about asymptotes. So you can see the connection between the asymptote and its convergence as a sequence or series, right? Then we go to the next question, and the next question says determine the infinite sum minus the sum of the finite, right? Because I say finite because in actual fact it's S of n, so basically it is a countable number. It is some number that we are ending at in the form of a b of n. They're not asking you to actually calculate this and to find ab equals n, but they're saying that the final answer should be a, or it has to be some sort of a number, and a b and an n, right? Okay, where Sn is the sum of n terms of the sequence, right? And so basically this one is a bit more straightforward. What you do is you use the formulas that you already know. You know the formula of the infinite sum, and that's a over 1 minus r, and it's minus a, it's a, and then for the finite sum, it is this formula over here, and then you just simplify, and you find that it's a of r of n, all divided by 1 minus r. Now, we are at this point, but remember what they wanted us to do. They want us to have an answer in this type of form, right? So since we want it in this type of form, what we can do now is just substitute the numbers. A is 10, R is 1 over 2, and then we just simplify, and you'd simplify, and you'd find that it is actually 20 times 1 over 2 to the n, and that is this form of AB of n, right? So that is the question 2 of that paper, right? Now question 3 is also continuing from there, and it says consider the series, and they give you a series where it starts from -3 plus 5 plus 13 plus 21 to n terms, right? And it says 3.1 as the question 3.1. It says determine the general term of the series in the form of t of k is equal to bk plus c. And I did mention this, that in actual fact we can view the arithmetic sequence as more of a linear formula, because you can see this looks like a normal straight line formula, right? But the only difference is that they use different variables. So when we calculate this, we actually do this. So let's first remember this is a series. Let's first rewrite it as a sequence, and when we rewrite it as a sequence, we have -3, 5, 13, 21, and then we get the first difference, and which is 8, and so our variable b is equals to 8, and then since we know that that is 8, we can just substitute it into the place of b, and then we are left with tk is equals to 8k plus c. But now what do we do here? Now we need to look back at the sequence and choose any of the possible terms that you'd like, and then you substitute. For me, I chose 13, which 13 is the third term, so it's t3, and then it's equals to 8 of 3 plus c, and then you can see that in actual fact 8 times 3 plus c is equals to 13, and then we just solve for c and we get 11, and then once we have 11 we just rewrite it, -11, sorry, then we just rewrite it as t of k is equals to 8k minus 11. And then the next question says write Sn in sigma notation, and if we have to write it in sigma notation, this is the sign for sigma notation, and it is the S of n. So the n is the last number or the final number that we are looking for. So in actual fact, we put the n at the top because it is the last number, and then the bottom number is k equals 1. We said k equals 1 because our formula of t of k is in k, right? It's in terms of k. So we start at k equals 1, and then we just place our formula near the sigma notation, and then you're done. So that is the answer for that one. And then 3.3 says show that Sn is equals to 4n minus 7n. Now they just want us to show that the sum, right, the sum of n is when you simplify it is 4n squared minus 7n. And what does that mean? We already have almost everything. So there's the formula for a general sum, arithmetic sum, and the general formula for the arithmetic sum is n over 2 to a plus n minus 1 and d, right? So what do we do here? Now, since we already know our d, it's 8, and then it's minus 1, it's n minus 1, and we know our a, it's 3, it's -3, but -3 times 2 is -6, and then we have n minus 2, n divided by 2, sorry, and then you just simplify, and you'll simplify, and you'll find that in actual fact it is 4n squared minus 7n. Now, there are just a few more things that I need to mention. Remember, we have two formulas for the arithmetic sum, right? And this is the first one and the second one. Here's the second one here, where we have the first term and the last term. But here, the interesting thing here is that the last term, since we are talking about the nth, we don't know what the last term is. It really depends on the nth. So the last term here is literally the formula itself. So it's 8k minus 11, but in this case we'll say 8n because they're looking for the sum in n. So it's n minus 11, and then you'll find that in actual fact this is a more quicker calculation compared to using this formula over here. So you actually do find the same thing. Or you could have noticed that in actual fact now that the addition or the sum of these numbers makes a quadratic pattern, right? What do I mean? Remember, the first term is negative 3, but the second term is plus 5, right? So if it's negative 3 plus 5, that gives us 2, and so on and so forth. And so, sorry, that gives us 2, and then it gives us 15, and then it gives us 36. And then you get the first difference, second difference, and then you get your answers, and then you use your second difference, and you use how you usually calculate your quadratic pattern, using your a plus b plus c to give you one of the variables, 3a plus b, and 2a to give you a, right? And so these are the three methods that you could have gone for when solving this problem. Okay, now we go to 3.4. Now in 3.4 it's quite interesting. Now in 3.4 it says another sequence is defined as, right? So it says q1 is equals to negative 6. It says q2 is equals to negative 6 minus 3. It says q3 is negative 6 minus 3 plus 5. It says q4 is minus 6 minus 3 plus 5 plus 13. Here it also says q5 is minus 6 minus 3 plus 5 plus 3 plus 21. Right. Now there's something that is actually happening here that is quite interesting. If you had to, now, okay, let's first read the question. So 3.4.1 says, write down the numerical expression. So they're not actually looking for a single number. They want you to write it out as it's written out here as an expression, right, for Q6. So it's the next one. So now, how do we find the next one? So if you look at this, it says minus 6, and then it's minus 6 minus 3. The difference between this is 3, right? So in actual fact, it's minus 6 plus 3 to give you negative 3, right? But then from minus 3 to 5, then it's actually 8. And then from 5 to 13, it's 8 again. And then 13 to 21, it's also 8. So in actual fact, from 21 to the next number, it should be plus 8, which we could say now it's 29. So that is the easiest way that you could have figured that one out. So it's actual fact, the expression that you write out is negative 6 minus 3 plus 5 plus 13 plus 21 plus 29. Okay, and now we look at the next question. So the next question here, this one here, it says calculate the value of Q129. So Q129. How can we do Q129? Now firstly, notice something again. When you did 3.4.1, you notice that in actual fact the difference between 6 and negative 3 was different. Is different from all the other numbers where we started from negative 3 to 21, right? Because the difference, the first difference for all of these is 8. But this one here, it is not 8, it is 3. So in actual fact, if you think of it, you have already done this one, this part over here, which is from negative 3 to 21 and to that finite number. It is exactly the same as the one that we started off at the top. And we had already calculated the sum, the finite, or the sum, or the finite sum of this particular expression, right? And this expression holds true for all the rest except negative 6, right? It holds true for all the rest except for negative 6. So you could imagine that in actual fact, if we said it is Q2, then we could have said it's minus 6 plus what? S1. And this S1 is from this formula. So if you put 1 in the place of n, you would find that it's negative 3. And so on and so forth. So if it's Q3, then it is minus 6 plus S2, right? It's Q3. And so on and so forth. So now they're asking us for Q129. So if it's Q129, then what does that mean? We can say now it's -6 plus S128, and we already know this formula. There's the formula over there, and then we just plug in 128 minus 6, and then your calculator will give you the final answer, which is 64,634, and that would be your answer to Q. And now, notice something here that I just wrote a quick scribble, is that in actual fact, if you add all these numbers together, if you add, this is -6, this one is -9, and so on and so forth. So if you add all these numbers and write them as a single number of Q, and you write them as a sequence, then you can see that in actual fact, you can do it as a quadratic sequence, and by doing it as a quadratic sequence, you get the first differences and the second differences, and then you use your a plus b plus c, your 3a plus b, and 2a to give you a formula for Qn. And once you have the formula for Qn, then you place Q129, and then you'll find your answer. So that is the questions that we wanted to look at today. And so I really hope this was helpful. I really hope that you understood all the stuff that we did here. But other than that, I really thank you for the time that you have given to look at the part 1 and part 2. I'll see you next time. And another thing is that there will be content that will be uploaded onto the channel, and some of the content that will be uploaded onto the channel will also do grade 11 and grade 10 work. But on the descriptions, please look at the descriptions and also subscribe. Please look at the descriptions, because in the descriptions you'll find other links to other content. For instance, with this particular topic of sequences and series, we do have an article or a blog that is posted on our website, where we talk about the 7 interesting or amazing things about sequences and series. So I really thank you, and I'll see you next time. Oh, and do follow us on our Facebook page. Thank you. Bye.